We send rovers to roam the orange sands of Mars, millions of kilometers away. The James Webb Telescope peers through a cosmic keyhole, capturing light from galaxies born 13 billion years ago. But if you stepped onto the deck of a ship in the middle of the Pacific Ocean right now and looked down, you'd be staring at an absolute blind spot. The surface of Mars is mapped more accurately than the floor of our own seas. We know more about the craters on the Moon than about the colossal scar that's splitting our planet apart right now. And at the center of this collective scientific failure lies one specific point: the Challenger Deep. Imagine a commercial airliner cruising 11 kilometers above your head. All you see is a thin white contrail against the blue. The Mariana Trench drops down exactly that same distance. If you flipped Mount Everest upside down and sank it into that abyss, there would still be 2 kilometers of freezing water above its sharp peak. The pressure down there is 1,086 bars. That's 11 million grams pressing on every square decimeter. Picture a heavy SUV trying to balance one wheel on a single tiny Lego brick. Now imagine that brick is your finger. The deep isn't just hostile. It's a hydraulic press on a planetary scale. Everyone thinks the Mariana Trench is just a deep, dark, cold ditch at the bottom of the ocean. And everyone is wrong. It's a chemical reactor where water compresses into a dense gel, skeletons dissolve in hours, and life exists in defiance of thermodynamics. This is a video dive. We'll peel back 6 layers of the familiar, from the salty air at the surface to the metallic grating 11,000 meters down. And when we finally reach the bottom, you'll understand why humanity is so terrified of its own planet. Before we take that first step into the abyss, hit subscribe. We're descending into a place no one comes back from. From above, the ocean looks like a perfect blue vacation backdrop. Sunlight sparkles lazily across the waves, a salty breeze tickles your face, and the warm water seems like the height of hospitality. It's a facade, a cheap planetary marketing trick. The real ocean starts where that party glitter fades, and it happens terrifyingly fast. The human brain is used to measuring space horizontally, but the vertical axis breaks our perception settings within the first few minutes of descent. The first 200 meters down, marine biologists call the euphotic zone. There's still enough sunlight here to drive photosynthesis, and the water is warmed by surface currents. This is the world we're used to seeing on nature documentaries and in diver photos. It's familiar, predictable, and safe. Dolphins swim here, coral fish dart around, and tourist boats cruise above. But the moment you cross that 200-meter line, the scenery starts to collapse. You enter the mesopelagic, the twilight zone of the ocean. This is where the physics of optical selection begins. Water works like a giant selective light filter, ruthlessly eliminating spectrum after spectrum. The first to go is red. Its wavelength is too long, its energy too weak to punch through the density of water. Red disappears at just 15 meters down. If you cut your hand at that depth, instead of the familiar scarlet, you'd see a thick, murky green or almost black liquid. It's a horrifying sight, disorienting. Your body screams danger, but your eyes see an alien, swamp-like substance. After red, in a mass grave of photons, orange, yellow, and green vanish in sequence. At 300 meters, the world becomes completely monochrome, painted in dull, leaden blue tones. Blue holds out the longest. Its short, high-energy waves penetrate the water column deeper than any other. But they, too, are doomed. Heat disappears, along with the light. The boundary between sun-warmed surface waters and the icy abyss is called the thermocline. Crossing this zone physically feels like a sudden punch. Water temperature drops from a comfortable 25 degrees Celsius to 3 or 4 degrees in just a few dozen meters of descent. This isn't gradual cooling, it's a sharp thermal barrier, like stepping out of a hot sauna straight into an ice hole in the middle of winter. Your breath catches, your blood vessels spasm, and your skin breaks out in a cold, clammy sweat from the primal fear of the encroaching cold. At this same point, another force begins to grow, the one that ultimately makes the Mariana Trench unconquerable: pressure. Every 10 meters of descent adds exactly 1 atmosphere of force to your body. At 500 meters, every square centimeter of your skin is bearing 50 kilograms. That's the weight of a full-grown wolfhound sitting on an area the size of a postage stamp. Your lungs compress, the volume of air inside them shrinking 50 times. A person without special equipment at this depth would have been turned into a broken doll with ruptured internal organs by the first third of the descent. To understand how everyday objects behave under this force, oceanographers often run a simple but vivid experiment. They tie an ordinary styrofoam coffee cup, with a funny face drawn on it in marker, to a deep-sea submersible and send it down. Styrofoam is made of tiny air bubbles trapped in thin polymer walls. At a depth of around 1,000 meters, where pressure reaches 100 atmospheres, that air compresses so violently it destroys the material's structure. When the sub returns to the surface, the cup looks like it was shrunk at a quantum level. It ends up the size of a thimble, a dense, hard piece of plastic with no pores left. All the writing on it remains in perfect proportion, just 5 times smaller. The abyss doesn't break things chaotically. It neatly and relentlessly compresses them, squeezing out every pocket of emptiness. At the 1,000-meter mark, light dies for good. No solar photon can punch through this kilometer-thick layer of liquid lead. You enter the zone of pure ink, the bathypelagic zone. Here, there is no concept of day or night, no seasons, no yesterday or today. Eternal, ringing darkness, ruled by a cold of around 2 degrees Celsius. Most people are convinced that in this absolute darkness, nothing can be seen. But they're wrong again. The darkness here isn't empty, it's alive and shimmering. The creatures of these deeps have turned darkness into a weapon and a means of communication using bioluminescence. Chemical reactions inside their bodies make the surrounding water burst with cold blue, green, and yellow sparks. Giant squid use flashes of light on their bodies to blind prey. Deep-sea anglerfish light up their ghostly lures dangling right in front of their toothy jaws. The Twilight Zone feels like a nighttime metropolis during a total blackout, where only the occasional car headlights and neon bar signs still glow. It's a terrifying, cold beauty. It beckons you in, but every single spark is a death sentence for anyone who dares to get too close. You're standing on the edge of the Challenger Deep. Beneath you, there are another 10 kilometers of absolute emptiness, filled with water whose density begins to change under the pressure, taking on new physical properties. Down here, water no longer feels like a soft liquid. It becomes a viscous, heavy medium through which sound travels at a speed 4.5 times faster than it does in air. The abyss is waiting. At a depth of 8,000 meters, the ordinary laws of chemistry and biology that we take for granted on the surface stop working. School textbooks tell us that water is incompressible. Physicists in labs nod in agreement. But the Mariana Trench couldn't care less about classroom theory. Under a pressure of 1,000 atmospheres, water molecules are squeezed so tightly together that the volume of the water shrinks by about 5%. This changes everything. The water becomes denser, heavier, and more viscous. For microorganisms, moving through this environment feels like trying to swim through liquid motor oil. This is where the real oddities of biology begin. The main enemy of any living thing at this depth isn't the cold, and it isn't the lack of light, it's protein denaturation. All life on Earth is built on protein molecules. Imagine a protein as an incredibly complex piece of origami, folded in a precise order and held together by fragile hydrogen bonds. When the pressure exceeds a critical threshold, the dense, viscous water molecules start literally squeezing themselves inside that paper crane, breaking the bonds and turning the orderly structure into a shapeless clump of chemical junk. It's like boiling an egg in a frying pan. The protein curls up and loses its properties. Only in the abyss, this happens without any heat. The cells just stop functioning and die. Evolution solved this problem in an elegant and cynical way. Deep-sea organisms use a special chemical shield, a molecule called trimethylamine N-oxide. This molecule works like a physical stabilizer for the protein origami. It binds the water molecules around the protein, creating a rigid water cage and preventing them from penetrating the structure. It's because of this substance that deep-sea fish smell much fishier than a freshwater carp. That smell is a byproduct of the breakdown of that protective compound. But this defense mechanism has a hard physiological limit. The deeper a creature goes, the higher the concentration of trimethylamine N-oxide needs to be inside its cells. At around 8,200 meters, you hit a critical tipping point. The concentration of this compound in the fish's body gets so high that its cellular fluid becomes hyperosmotic compared to seawater. In plain English, the fish's cells become saltier than the ocean itself. Water from the outside starts rushing in through the cell membranes, trying to dilute that concentrate. The cells can't handle the osmotic pressure. They swell up and burst from the inside. This is a fundamental chemical barrier for vertebrates. Because of it, no fish can physically exist at the very bottom of the Mariana Trench. The deepest dwelling fish on the planet, the Mariana snailfish, has been recorded at 8,178 meters. Beyond that lies an evolutionary no man's land. Only invertebrates and single-celled organisms live deeper, creatures that took a completely different path in building their bodies. The abyss delivers a second blow to skeletons and shells. At 5,000 meters deep, the ocean crosses an invisible line, the carbonate compensation depth. Because of the freezing temperatures and crushing pressure, the water sucks up huge amounts of carbon dioxide. The chemical balance shifts, turning the bottom water into a weak but highly aggressive carbonic acid. Ordinary calcium carbonate, the stuff mollusk shells and animal bones are made of, dissolves in this environment as fast as sugar in boiling water. Life on the seafloor has essentially had to ditch bones entirely. The local amphipods and xenophyophores build their shells out of silicon, heavy metals like barium, and organic chitin. They create glass skeletons. These are fragile, translucent creatures whose bodies look like living crystal. At 11 kilometers deep, you won't find a single hard shell. If you step on a local inhabitant, there's no familiar crunch of bones under your sole, just a soft, jelly-like squish. And yet, despite the total absence of sunlight, the bottom of the trench is still teeming with life. We tend to think that without photosynthesis, life is impossible. That's an illusion. Deep in the dark fissures of the Mariana Trench, a process occurs that scientists call serpentinization. There are no volcanoes or glowing lava here, but there's immense tectonic pressure. Water seeps through cracks in the Earth's crust, traveling up to 20 kilometers deep until it reaches the upper mantle. There, it comes into contact with peridotite rock, rich in iron and magnesium. A violent chemical reaction follows, releasing heat, hydrogen, and methane. The rock swells up, transforming into serpentinite, while the gases rise back up to the ocean floor. These gases are toxic to any land creature, but for deep-sea bacteria, they're the equivalent of sunlight. The microbes oxidize the methane and hydrogen, kickstarting a process called chemosynthesis. They build organic matter literally from rock and poison. These bacterial mats, looking like white slimy mold on black stones, form the foundation of the entire abyssal ecosystem. It's a completely self-contained world. If our sun went out and Earth got buried under a mile of ice, the inhabitants of the Mariana Trench wouldn't even notice the cosmic catastrophe. If you've made it this far and your brain hasn't boiled yet, write "abyss" in the comments. I need to know who's coming with me all the way to the bottom. The ground beneath our feet feels like solid, unchanging Earth. That's an illusion. Our planet is in a state of constant geological churn. It's just happening on a scale far too vast for a short human lifetime. The Earth's crust is broken into giant tectonic plates that are constantly creeping across the surface of a semi-molten, scorching mantle. The speed of this movement is almost nothing, about 6 centimeters a year. That's exactly how fast your fingernails grow. Sounds harmless, but when plates weighing trillions of tons collide, that snail's pace triggers disasters on a planetary scale. The Mariana Trench is a giant tectonic scar. It's the place where the ancient, heavy Pacific Plate rammed into the younger, lighter Philippine Plate. The Pacific Plate never stood a chance in that head-on collision. It was older, colder, and therefore much denser than its neighbor. It lost the tectonic battle and began slowly sliding under the Philippine Plate, diving down into the planet's scorching interior. That process is called subduction. And where one plate breaks over another and dives beneath it, a curved depression forms, a long, narrow, and incredibly deep trench on the ocean floor. This process has been going on for millions of years. It comes with enormous friction. Huge slabs of basalt grind, crumble, and melt miles beneath the surface. That generates the most destructive earthquakes on Earth. The trench isn't just a static hole. It's a zone of endless seismic warfare, a place that, at any second, can trigger a tsunami wave powerful enough to wipe entire cities off the map. For a long time, humanity had no idea this tectonic rift even existed. Back in the 19th century, British sailors aboard the corvette HMS Challenger decided to measure the depth of the Pacific Ocean. They didn't have sonar or computers. All they had was a hemp rope several kilometers long with a cast iron weight at the end. The sailors manually paid out that line over the side, watching the tension for hours. When the weight hit the bottom, their instruments showed an incredible number for the time, over 8,000 meters. The world didn't believe it. The scientific community decided the rope must have been dragged sideways by a deep-sea current. It took nearly a century before anyone dared to go down there in person. In the 1950s, the world was swept up in a technological frenzy. The Cold War was on. The US and the USSR were competing in everything, from nuclear warheads to space satellites. But there was another, less obvious race, the race to the center of the Earth. The military understood that a submarine that could hide at extreme depths would be the ultimate invulnerable weapon of retaliation. In that atmosphere of paranoia and discovery, a Swiss physicist named Auguste Piccard appeared on the scene. He was a man of extremes. In the 1930s, he built a stratospheric balloon and personally ascended to an altitude of 16 kilometers, documenting the curvature of the Earth's crust. Having conquered the sky, he set his sights on conquering the abyss. Piccard invented the bathyscaphe, a fundamentally new type of submersible. Previous deep-sea spheres were lowered on cables from ships, which was deadly dangerous. If the cable snapped, the crew was doomed to a slow death by suffocation. Piccard's bathyscaphe was autonomous. It worked on the principle of an underwater airship. A massive float filled with lightweight gasoline supported a heavy steel gondola carrying the crew. For descent, they used heavy metal ballast held in place by electromagnets. In case of an emergency and a power failure, the ballast was automatically released and the bathyscaphe would rise on its own. The vessel was named the Trieste. Funding for its construction came from the US military, who planned to use deep-sea research for underwater warfare. Piccard handed over the pilot's seat to his son, Jacques. His partner was US Navy Lieutenant Don Walsh. On January 23, 1960, they began their legendary descent into the Challenger Deep. The dive took nearly 5 hours in total darkness. Two men sat inside a cramped steel sphere just over 2 meters in diameter, curled up in a fetal position. Around them was freezing water, its temperature quickly dropping to just above 1 degree Celsius. Condensation dripped from the ceiling of the gondola straight down their necks. The sphere's walls, 12.5 centimeters thick, groaned under the immense pressure. The metal deformed, compressing under the weight of the water. At a depth of 9,000 meters, a deafening explosion rang out. The sound was so loud that the pilots were certain their sphere had cracked. The entire hull of the bathyscaphe shuddered. As they later discovered, due to thermal contraction, the steel hull had shrunk faster than the outer plexiglass window of the entry tunnel. This caused a critical deformation, and the plastic cracked along its entire length. Any normal person would have hit the emergency ballast release button right then, but Piccard and Walsh looked at each other and made the decision to continue the descent. It was madness bordering on suicide. The crack didn't grow, and the bathyscaphe kept slowly sinking into the darkness. They touched the bottom at a depth of 10,916 meters. Soft beige silt billowed up in a cloud around the submersible. In the light of the floodlights, Piccard saw something that would change biology forever. A flatfish resembling a flounder. Life existed where it should have been impossible. They spent just 20 minutes on the bottom. The crack in the porthole threatened to give way with any change in conditions, so the pilots began their ascent. The return to the surface went smoothly, but instead of triumph, they were met with obscurity. Humanity had turned its gaze to the stars. A year later, Yuri Gagarin flew into space, overshadowing their quiet victory over the abyss. Ocean exploration was scaled back. There followed a 52-year chronological gap, half a century of silence at the bottom of our own planet. After 52 years of silence, the abyss opened its doors once again. The man who dared to break that half-century pause wasn't from the scientific community or the military. It was James Cameron, the director behind the highest-grossing films in cinema history. For Cameron, the ocean was never just a hobby, it was an obsession. He made 33 personal dives to the Titanic wreck, developed unique deep-sea cameras, and spent 7 years of his life and $10 million of his own money to build a one-of-a-kind submersible. His bathyscaphe, the Deep Sea Challenger, looked like something out of sci-fi, a narrow, bright green vertical torpedo over 7 meters tall. Unlike the spherical Trieste, this vessel descended vertically at the speed of a professional diver. Inside the torpedo was a tiny, high-strength steel crew sphere. There was so little room that Cameron had to sit with his knees tucked tightly under his chin. No partner, no backup, just total, ringing solitude inside an iron capsule in the middle of the endless ocean. On March 26, 2012, Cameron began his journey downward. At 8 kilometers deep, the hull started making sounds that the director later called the most terrifying he'd ever heard. The metal was compressing under the weight of the ocean, groaning with a deep, vibrating moan. It was the physics of deformation under 800 atmospheres of pressure. The cabin walls squeezed inward, shrinking by several centimeters. In that moment, the pilot fully grasps the cost of a mistake. If there was even the tiniest microscopic flaw in the sphere's shell, death would come instantly. Implosion, a reverse explosion under pressure, turns the submersible and its pilot into a uniform mass in 2 milliseconds. The human nervous system takes about 10 to 15 milliseconds to send a pain signal from the skin to the brain. You physically wouldn't have time to realize you were dying. Your body would cease to exist faster than your brain could register the disaster. Cameron kept descending through that metallic screech. He hit the bottom at 10,908 meters. The first thing he saw through the porthole was absolute emptiness. No monsters, no sea creatures, just a vast, flat, dead plain of beige silt. Cameron described the feeling like being on another planet, complete sensory deprivation. The edge of the floodlights only revealed a few meters of space, beyond which stood a wall of eternal, ink-black darkness. The pressure disabled the hydraulics of the robotic arm, and the intense cold drained part of the batteries. After collecting a few sediment samples, Cameron began his ascent. He proved that modern technology could make deep-sea dives manageable. 7 years later, that success was cemented by Victor Vescovo, an American billionaire and professional explorer. He commissioned the submersible Limiting Factor with a titanium hull 9 centimeters thick. Vescovo turned extreme dives into routine. He descended to the bottom of the Mariana Trench multiple times, spending up to 4 hours there and gathering unique scientific data.
Именно эти экспедиции заставили ученых из НАСА всерьез заняться изучением земных глубин. Астробиологи поняли, Марианская впадина – идеальный аналог ледяных миров Солнечной системы. В первую очередь, спутника Юпитера Европы и спутника Сатурна Энцелада. Под многокилометровой ледяной корой этих небесных тел скрываются глобальные океаны жидкой воды, которая контактирует с каменистым ядром. Давление на дне океана Европы почти такое же, как в Марианском желобе. На дне нашей впадины ученые нашли микроорганизмы, которые живут прямо внутри твердых горных пород на глубине 10 километров под дном. Они питаются чистым водородом, который выделяется в процессе серпентинизации. Им не нужно солнце, не нужна органика, падающая сверху. Они существуют в полной изоляции от остальной биосферы Земли. Если жизнь смогла закрепиться и эволюционировать в каменных тисках под давлением в 1000 атмосфер на нашей планете, у нас больше нет причин сомневаться, что она существует на Европе. Марианская впадина доказала, жизнь во Вселенной — это не редкая случайность, требующая идеальных тепличных условий.
Жизнь — это агрессивный геологический процесс, который способен пробить себе дорогу сквозь любые уровни давления и холода.
Мы ищем инопланетян в далеком космосе, игнорируя тот факт, что их полные аналоги живут прямо у нас под килем, в ледяной воде Тихого океана. Наш след на планете глубже, чем наши самые смелые научные амбиции. Когда Виктор Висково в 2019 году коснулся дна бездны Челленджера, он ожидал увидеть первозданный, нетронутый эволюционный заповедник. Мир, скрытый от человеческой суеты 11 километрами жидкой брони. Вместо этого, в свете мощных светодиодных прожекторов, его титанового батискафа показался обычный пластиковый пакет из супермаркета и несколько цветных фантиков от конфет. Они лениво лежали на светлом палевом иле. Это был шок, отрезвляющее столкновение с реальностью. Вы тратите годы жизни, миллионы долларов, привлекаете лучшие инженерные умы планеты, чтобы покорить самую глубокую точку Земли, а вас там уже ждет бытовой мусор. Марианская впадина работает как гигантская гравитационная воронка океана. У нее нет выхода. Все, что попадает на поверхность воды в любой точке Тихого океана, рано или поздно начинает свой медленный, бесконечный путь на дно. Органический мусор, трупы рыб, медуз и китов распадаются, превращаясь в так называемый морской снег. Этот непрерывный дождь из белых хлопьев падает в бездну миллионы лет. Но сегодня вместе с органикой вниз летит техногенный пепел нашей цивилизации. Микропластик стал новой геологической породой океанского дна. Это крошечные частицы полимеров размером меньше 5 мм. Они образуются, когда выброшенные нами бутылки, пакеты и рыболовные сети разрушаются под действием ультрафиолета и волн. Эти частицы не растворяются, они пропитывают толщу воды. Глубоководные рачки-амфиподы, которые кишат на илистом дне впадины, не могут выбирать пищу. Они едят все, что падает сверху. В 2019 году группа британских исследователей детально изучила образцы амфиподов, выловленных с глубины 10 тысяч метров. Результаты оказались пугающими. В желудках абсолютно каждого исследованного существа были обнаружены синтетические волокна пластика. Животные на дне мира буквально состоят из нашего мусора. But plastic is just the tip of the iceberg. The real catastrophe is invisible to the eye. The Mariana Trench accumulates persistent organic pollutants.
Back in the mid-20th century, the chemical industry mass-produced polychlorinated biphenyls and polybrominated diphenyl ethers. They were used everywhere, from cable insulation to paints and plasticizers. By the end of the century, these substances were officially banned because of their extreme toxicity and cancer-causing potential. But it was too late. Millions of tons of these compounds had already entered the global ocean. PCBs barely dissolve in water. They're lipophilic, which means they easily bind to fats and organic particles. Attaching to marine snow, these poisons sink fast, concentrating right at the bottom of deep-sea trenches. They simply can't evaporate or escape into the atmosphere. The concentration of these harmful substances in the bodies of amphipods from the Mariana Trench turned out to be 50 times higher than in crustaceans living in the Liaohe River Delta. For context, the Liaohe is one of China's most polluted industrial rivers. The deepest, most isolated corner of the wild turned out to be chemically dirtier than an industrial drainage canal. This isn't just a local environmental drama, it's a closed loop that hits us right back. Microplastics in the water act like a sponge. They attract and absorb toxic chemicals on their surface. Small crustaceans eat that poisoned plastic. Deep-sea predators eat those crustaceans, and these toxins climb right up the food chain. Many fish species make vertical migrations, rising to the surface at night to feed, and dropping back down during the day. The poisons we dumped decades ago take a round trip through the food web and end up back on our plates as expensive tuna fillets or sushi in a downtown restaurant. The ocean returned our debt with interest, but the abyss can strike back with more than just chemical weapons. It's got its finger on the trigger of global tectonic disasters. The subduction zone of the Mariana Trench is a giant spring under constant compression. The plates don't slide smoothly. Their rough edges catch on each other, building up colossal stress in the rocks over centuries. When the rock's breaking point is exceeded, there will be an instantaneous shift across thousands of square kilometers. That's a mega-earthquake of magnitude 9 or higher. It will instantly raise or lower a massive slab of the ocean floor, displacing trillions of tons of water. A tsunami will form, racing across the open ocean at jetliner speed, over 800 kilometers an hour. Coastal countries won't have time to evacuate. The abyss can destroy entire megacities in minutes just by snapping one tectonic fold. We live on a powder keg, but we'd rather not notice. Space has officially won the war for our imagination. That's just a fact. We're willing to spend tens of billions of dollars to send another tin can to photograph the rusty sands of Mars or distant gas giants. NASA's budget exceeds $25 billion annually. China spends about $12 billion on its space program. Meanwhile, the entire global budget for deep ocean exploration doesn't even reach $1 billion. One single Mars rover costs more than all of humanity's deep-sea manned programs over the past 30 years combined. This is a choice we've made as a species. We decided to look up, deliberately turning our backs on what's happening right beneath our feet. The reasons for that choice are simple and cynical. Space is photogenic. It's beautiful, romantic, and promises new worlds for our distant descendants. The deep is dark, cold, and terrifying. On Mars, you can plant a national flag and broadcast it live to the entire world. At the bottom of the Mariana Trench, you'll be greeted by nothing but an endless pale plain, where your spotlights only pick out a few meters of murky sediment. The space race inspires kids to become astronauts. The abyss gives them nightmares. By refusing to study the depths, we're making a colossal mistake. The ocean produces more than half of the oxygen you're breathing right this second. Deep-sea currents act as the planet's global air conditioner, distributing heat and shaping the climate on the continents. We're trying to design colonies on other planets without understanding how life support works on our own. The deep holds the keys to the medicine of the future. Extremophile bacteria living under 1,000 atmospheres of pressure produce unique enzymes. Their molecular structure is stable under extreme conditions that would instantly destroy ordinary proteins. These enzymes are already used for PCR tests and molecular diagnostics. Today, scientists are studying deep-sea organisms to create a new generation of antibiotics capable of killing superbugs resistant to every known drug. It's possible that the formula for curing incurable diseases is being developed right now by microbes 8 kilometers down in total darkness. But we'll never know, because we don't have anything to get us down there. By the most conservative estimates of biologists, we've discovered less than 5% of deep-sea species. 95% of the creatures living in the abyss have never been seen by humanity. We share a planet with a vast, alien civilization of organisms whose existence we don't even suspect. The Mariana Trench is a perfect mirror of our society. It reflects all our greatness and all our pettiness. Our bravery, because we did manage to build titanium spheres and descend to the bottom of that deadly pit. Our stupidity, because we managed to poison the abyss with plastic and banned polychlorinated biphenyls before we even studied it properly. Our selectivity, because we stubbornly keep looking for traces of microbes in the waterless deserts of space while ignoring the overflowing source of life at the bottom of our own ocean. Life doesn't ask physics for permission. It doesn't play by our rules of comfort. It exists in absolute darkness, under millions of tons of water, feeding on poisonous gas and rock. And if it found a way to survive in the darkest, coldest, most hostile place on our planet, then it can survive anywhere in the universe. We just need the courage to look into that darkness. If this dive got you thinking, hit like and subscribe. There are plenty more places on our planet that people prefer to keep quiet about.